Okay, I think I will start. About 18 years ago, when I came into the industry, I was put into this intense training for Java, C++, data structure, RDBMS. Towards the end of it, I was supposed to present a project. And my table design looked something like this: employee name, city name, so on and so forth. And I was scored really bad. I was given a very poor score, and I asked them about it, and I was told the table design should look something like this, where you have the city name separated out, and you reference it back to your parent table. I was quite mad. To me, this sounded too complicated, unnecessary. I have to now write join queries. I have to learn join queries before I can write it. So naturally, I was mad. I was pushing back, which is when they told me a lot of reasons why this is a better design than my design. A lot of reasons were given, but the one reason that stuck well with me was that by doing so, I avoid a lot of repetition with the city name, and thus reducing the amount of data that is being stored, thus leading to cost optimization, reduce cost. Switching back to search technologies, where mapping or the design of the mapping is not really necessary because we have dynamic mapping, right? I'm just kidding. I'm just being sarcastic. Moving on. So this is a classic triangle that you would recall. Cost, performance, and shipping it fast. You can only pick two of it. So we will see about how you can still do the other two with still doing cost optimization. So I'll stop my philosophy here. Why should you listen to us? My name is Aswath, and go Priyanshi. You have.
Hi guys, my name is Priyanshi, and we are here to present today all about cost. Okay, so we are a part of Solution Architect team, and what we generally do, we work with several customers daily, maybe 100 of customers we have worked with, and most of them concerned about the cost, right? And which is along with performance, definitely, which we do. So that's what we are doing, and we are presenting here today. Okay, I'll move forward. Okay, so we wanted to build an agenda, but then we thought, okay, why so many boring slides, so many boring topics? Okay, so that's where we kept it empty. So we are looking at different aspects of cost, but you need to figure out, okay, how you want to do it, right? Someone could be very easy, someone could be the harder ones. Easier ones can be, maybe you can do it at a quick. You can figure out, okay, what I can do at my cluster today, and you can do them. But the difficult one, maybe tackle down slowly and figure out and solve them. Okay, let's get started. Okay, this is a big slide which we are seeing. Okay, so one of the key metrics which we look at is a CPU utilization on the domains, right? So if you see this metric, you see that graphs, right? There's a huge difference between max, min, and average. Okay, what that shows? So that shows node hotspot, or could be a node's hotspot, right? Because there's a big imbalance between different kind of nodes. Okay, in our cluster, what we do, we pick a same kind of nodes, right? Let's say we are picking 9 nodes or 10 nodes, right? We do get the same configuration. But what if they have imbalance in the resources, let's say the CPU, okay? The second slide which we see, which shows, okay, there are different set of nodes, but some of the nodes are having 94% of the CPU utilization, where some nodes are having just 65%. Or maybe I have some more nodes which are just using 40% of the CPU, right? Now, how do I save cost? How do I downscale my domain in this scenario? Until and unless I bring them to a balanced shape, right? All the nodes are serving the same traffic, same amount of resources. You cannot bring the cost down, because you cannot cut the cost for the nodes which are having 40% of the CPU, or maybe let's say less, right? So this is one of the important metrics which I would say a good to start, right? So today we are not telling you, okay, what are the thresholds or whatnot. We are just telling you, look at your domains, look at your clusters, and figure out how and what is happening inside them, if there are really some hotspots. Okay, so you can easily recognize that there are some APIs given above. You can look at them and you can figure out, okay, what's happening to my cluster. You can look at the thread pool, you can look at the nodes, you can look at the CPU. Moving to other metric. Okay, so another important metric, right, is the JVM, right, which we generally look at. So JVM alone is not the full metric which we should be looking, right? Because JVM comes, if you will be looking the same graph as a CPU, you might be seeing, okay, it's going up and down. But the better metrics to look at the JVM is garbage collection, GC, of the nodes. You will be seeing, right? So in this slide, you will be seeing there are different garbage collection metric for the different nodes which we have collected, right? Some nodes are having less time, less garbage collection, but some nodes are really taking a lot of time and having high garbage collection, right? Though this system is built out of JVM, out of Java, so we are using these concepts, and this is very important metric to look at, right? And then along with that, there are definitely different queries, cache, which plays a role, right? You will have request level cache, tier level cache, or query level caches, right? So we definitely need to look at how our garbage collection is being performed and how our JVM is behaving, right? This is another metric. We don't have a lot of metrics, but we are just telling you, okay, these are the things which you can start looking at to identify sweet hotspots. Another metric, which is very important, right? Customers do complain, okay, my indexing has been stopped, but I do have space in some of my data nodes or nodes, right? They don't see these kind of graphs. The last line you will see, right? There are a huge difference between max, min, and average. This again implies that some nodes are having maybe high amount of disk percentage usage, and some nodes are just free. They don't have a lot of data sitting itself, right? So customers are saying, okay, I have a space, why I can't use this? So this all implies to some of the best practices and the solutions which we are going to think or we need to see. And another metric is throughput throttle, right? This is also happening at different time on different nodes, okay? That means all of my nodes are not behaving same. I'm paying, as a customer, I'm paying the same cost for all nodes, but why? I'm not able to utilize them like 100% and all are not giving the same cost, right? So yes, this is what we need to figure out today. And now what if we saw, okay, we got these metrics, we saw, okay, there are node hotspots, there are some nodes which are not behaving well. Now what should we do now? So these are the results of the metrics which we saw. So most of these things, what we have seen, like in 80% of the scenario happens due to poor sharding strategies we have. Sharding is a very key aspect of any cluster. So what will happen if we'll have poor sharding, right? Like we saw in other graphs, right? That will lead to uneven data distribution over different nodes, okay? Uneven data distribution will cause storage skewness, right? Some nodes have good space and some nodes have bad space, and then they are not using their resources properly. And then with that, there will be storage skew, uneven load distribution on all the nodes. And then there will be uneven resource utilization, as we saw, okay, 100% CPU and then 40%. And eventually, as a result, we are seeing these graphs, right? The nodes are not behaving well. So it's very important to look at the strategies which we are performing while creating our clusters. Okay, so what are our sharding best practices? While creating any sharding strategy, we focus on three things majorly: the shard size, the distribution of shards over different nodes or over the cluster, and the third part is the replication factors is very important. So let's say first focus on the shard size. What is the best shard size I should be selecting for our domains, right? The general guidance says, okay, the shard size should be somewhere between 10 to 50 GB. But it varies on different workloads, right? Let's say I have an e-commerce workload. I am very super critical latency firm, so I need very small or very quick latencies in seconds or milliseconds or whatever, right? So the best practices says we should have 10 to 30 GB shard size for search critical workloads. And for log analytics, yes, latencies are critical, but we want to keep a lot of logs, a lot of data, right? So I cannot end up creating too many shards. So that's where we recommend to have 30 to 50 GB of shard size. Okay, so this is the one part. And the second part is the distribution. So you will see this node 1, node 2, node 3 are having the distribution. Let's say Apple is my index, Orange is my index, right? So I am evenly distributing all of my shards over all of the nodes I'm having in the cluster, right? What that gives me, the last graphs we saw, CPU having uneven distribution, disk having uneven distribution. So if I'll evenly distribute this, right, I'll be reaching to a point where my CPU is also evenly used. I have same amount of data in all the nodes, same amount of resources I'm trying to give. Such can vary on different aspects, but with this, right, we'll be able to reach at least a good part or an average of the shards. Okay, and third part is definitely the replication factors. What we always recommend to have at least replica for resiliency, which is the best choice. But if you also want to increase your QPS, right, so make sure that we are, and first and foremost, replicas are not sitting with the primary shard, so which is a good thing. And the second thing is, if we want to increase our QPS, let's enable and ensure that the replicas are not sitting in the same node where my other the same index is sitting, right? Which also helps, okay, to extract resources from those nodes. Other good things which we can implement to save a lot of cost is, and this is what we have seen a lot in multi-tenant workload, right? One of the thing and important thing is we put a lot of ISIMs. So customer has a use case, okay, I want to roll over my index, I'll do it maybe daily. So they end up creating too many shards, or maybe let's say I have 10 GB of data daily. So I'll end up maybe creating a daily shard for that 10 GB. So I'll be ending up a lot of shards at the month end. And that can harm, or that can cause a lot of resource utilization to my system, right? So instead of that, the best part is to have ISM rollover with the shard size or index size, right? Where you will be able to achieve, okay, I have a target shard size 10 GB, 30 GB, no matter, right? I have evenly distributed, no matter, let's say my index rollover happened tomorrow, but that is even. And that is of a particular size, right? Every day, if that is creating of, let's say index is getting created of 50 GB, that will be a particular size and evenly distributed on all of the nodes, right? So this is very important aspect, which we think, okay, daily rollover really works, but I think this we should be taking care in the cost optimization. We do have other scenarios. I would also invite Aswath with me. He will be explaining there are kind of multi-tenant workloads, how do we tackle them with different strategies and all, and will help us.
Thank you, Priyanshi.
No.
No? So the idea here is by rolling it over at the shard size, we make sure the shard size are consistent. So that's one of the key aspects for sharding strategy best practices. Another big problem that we often see is the multi-tenancy, right? So there's a lot of different type of indices for different log patterns, yeah, and it's not easy to have one ISM policy for every single one of it, right? So one thing that you can think about is splitting your different indices into different classes: high volume index, mid volume index, low volume, or you can even go finer than that, yeah, and have ISM policies separately for each of the classes. Or you can take it one step above by having the high volume in a different domain, mid volume in a different domain. So by doing so, high volume can be easily, the sharding strategy best practices can be implemented easily for high volume because they always are going to hit the 50 gig shard size before the time runs out for the retention period. Mid-volume, probably. Low volume may not be, but at least you reduce the blast radius on the number of indices that go off outside of your best practices. Yeah. Another thing that we implemented is the dynamic sharding strategy, which is basically looking at the ingestion rate and determining what is going to be the next sharding count for it. Yeah. So this is a thing that we implemented for one of the customers. We have a feature request open. That's the QR code. The feature request has a nice description of what exactly we did and how you can implement dynamic sharding strategy. Yeah. But the feature request is to actually have this feature natively available with OpenSearch, so you don't have to implement it outside by yourself. Yeah. Moving on, so this is a question that we get often. Yeah. When to do horizontal versus vertical scaling. Yeah. So let's use an example to go over this. Right. So on this side, I have 2 nodes of 64 gig memory each. On the other side, I have the same resource, but vertically scaled up, a tall node. So the question is, are they the same? Because they both are 128 gig of memory, but the question is, are they the same? The answer is, of course, yeah, they aren't, and that is because when you go over, or rather, let's take a step back. So we have 32 gig of heap space, or rather, half the memory is assigned to heap, and the remainder of the half is assigned to file system cache, right? So now, when you go over 32 gig of heap space, Java enforces you to use 64-bit reference pointer. When you're under 32 gig of heap space, Java lets you use 32-bit reference pointer, which is basically compressed OOPS, yeah? So what this also means is when you go over 32 gig of heap space, you need now more memory to store the same amount of data, which also leads to long GC pauses, yeah? So that is why these are not the same. And when talking about the memory allocation, there are 2 things that we always preach, right? One is both the heap and the off heap are equally important. So that is why we do half and half, 50%, 50%, right? We also do not go over 32 gig of heap space because of the said reason that I just informed. And that is why a 64 gig memory instance is a perfectly sized instance. Anything beyond that, you have to go horizontally. Until then, you can go vertically, yeah, if that makes sense. So there is always exceptions for everything, including this, and I will cover that when I get a chance. So I will not go over a lot into this right sizing because I see the time here, but this is basically what I just said. We go vertically up until 64 gig of memory, and sideways when we hit the 64 gig memory, right? So I said about the exceptions, right? So those are the exceptions where you can go over 64 gig of memory is when you look at the file system or file system cache, you look at the minor page fault, major page fault, if you see a lot of memory trashing happening, which is when you can actually make a case to go over 64 gig of memory, but still your heap size is still going to be 32. It's just that the extra memory that you have vertically on the system is going to go for your file system cache, yeah? So we always preach to look at the best practices documentation, yeah? But I'm going to show you one example here, right? So one of the line in the documentation says 25 shards per a gig of heap, right? So this means if you do the math, I believe about 800 shards can be kept on the same node. If we go by the 64 gig of memory thing that we just discussed, right? So we also see customers who have are close to hitting 1,000 shards on the same node, and we already know 1,000 shards is how much you can have on a node. And they want to know how to have more shards on the same node, right? And when you hit that point, you're already way too far off from the best practices, yeah? Because this is, the best practices says not to go over 24 shards per a gig of heap, yeah? But this is taken out of context, yeah? The actual best practices is to have at least 8 gig of memory per 100 gig of storage. And if you do 50 gig shard, you can actually have about 16 shards on a node that is perfectly sized. So imagine going from 16 to 800, yeah? So you get the idea. Another thing that we preach is the shard to CPU ratio, yeah? So we say at least have 1.5 vCPU per every active shard that you have. This could get expensive, so if you want to be aggressive about it, you can go 1.25 vCPU or even 1 vCPU per shard. But once again, yeah, it's about the active shards, not the number of overall shards that you have. Because if you calculate for the overall number of shards you have, it's also going to get expensive too fast. Active shards actually mean when you roll over, let's say you have 5 shards and you roll over every day, yeah, your active shards is actually 5, not the different rollovers that you already have had in the past, yeah. Just giving you an example. Dedicated master node, once again, not going too much into it, but we have a documentation page in the Amazon OpenSearch documentation that actually says the dedicated master node sizing, yeah. We see a lot of customers, once again, following the best practices. They have the dedicated master node as it's been set. In spite of it, they see a lot of, let's say, a lot of JVM memory pressure in their master node. On investigation, usually what we find is the master node is actually cluster, the cluster state is very heavy, yeah. Why would the cluster state be very heavy? Probably you have a lot of mapping. The mapping is exploding, or you have a lot of alias. There's a lot of things that are going on. So it's basically not the master node is incorrectly sized. It is because your workload is not optimized. So master node not being rightly sized is more of a symptom and not you following the best practices, yeah, if that makes sense. Moving on, there is a lot of problems that we can talk about, but of course, that's not possible to talk about every single one of it, right? So what we thought is to give you a perspective, yeah? So let's see how we approach a problem, yeah? So let's say the problem is this throttling. What would you do, like John Kenyanas, yeah? So would you increase the IOPS and throughput, give extra provisioning, or would you overshard it or have more shards on more nodes to reduce the IOPS and throughput on the nodes? Or would you identify and resolve the root cause of the problem, which is in this case this throttling? Or would it be all of the above, but in some sequence, yeah? Once again, we see a lot of customers directly opting for A because it's easier, yeah? Some customers do B followed by A, which is not too bad, but our preaching is always going to be identify why this throttling is happening in the first place. It could be because your segment merges are happening too often, and that could be because you're doing a lot of updates, or your refresh interval is too large, or your bulk payload is too big, yeah? So it could be literally anything, or you could be doing a lot of export using scroll API or with search after. So the important takeaway here is to actually identify the root cause of a given problem, and not simply doing a patchwork of increasing more resource for a given problem, yeah? The problem could be literally anything, right? It could be, I don't know, CPU spiking or JVM memory pressure. JVM memory pressure could be because you're using a lot of nested documents, or it could be because, once again, you're using a lot of painless script, yeah? So the solution should not be adding more JVM by one way or the other, but the solution should be understanding why the JVM memory pressure is happening in the first place and going after the problem. Yeah, that should be the ideal approach, yeah? Moving on, switching tracks here, such performance. So for this, once again, let's use an example. Let's say you have a one node cluster that has only one index, that has only one shard, yeah? And this node has 10 vCPU. So you see the formula over there, and that gives you 15 such thread pools. What this actually means is you are able to run 15 such threads at any given second. So let's say every such request that is coming to the system takes exactly 1 second. If that is the case, you are able to run 15 searches at that given second, yeah? And this is called QPS, queries per second, yeah? So how do you improve your QPS? How do you accommodate more searches to be run in concurrently? So there are two things that you can do on a high level. One is, so basically you need to reduce the search latency. So if you reduce your search latency from 1 second to half a second, let's say, now all of a sudden you're able to run 30 requests with the same resource, right? Or if you only need 15 search requests per second, you can cut down the 10 vCPU to 5 vCPU. leading to cost optimization, right? So there are two high-level ways that you can achieve lower search latency. One is writing effective search queries, yeah. The other one that you probably saw earlier when Pallavi was presenting, yeah. Just an example, just by keeping up with the version upgrade, if you're a heavy user of date histogram, as you see here, you're dropping from 6 seconds in version 1.3 to all the way down to 100 milliseconds if you're just keeping up with the version. Reduced search latency leads to more QPS or reduced CPU usage. Yeah, this is how you do cost optimization. Yeah, there's no magic. Yeah. So cost saving, once again, there's a lot of things to talk about, but we can only give example given the short duration. I know we are running out of time, but there's so much to talk about it. So let's use an example. And the example that we are going to use is mapping optimization, because if you were at the beginning of the talk, I was trash talking about the mapping. Yeah. So mapping optimization is something that we talk about to our customers often. Yeah. The first thing that I always say is to find a balance between frugality and flexibility. If you're using dynamic mapping, you're 100% flexible, 0% frugal. If you're using a static mapping, the dynamics change. Yeah? It is important to understand appropriate field types to be used. When you're using static mapping, you take control of the mapping. You find appropriate field types for the fields that you're using. Understanding the difference, I'm just giving examples. Understanding the difference between match versus match-only text. Understanding when to use date nanos. If you do not need nanosecond level difference for sorting, don't use date nanos. Yeah. Or another example, if you have an employee address field, and if you're marking it as both keyword and text, there is no reason to have employee address as keyword, because you're not going to run aggregation, you're not going to run sort queries on those fields. So taking control of your mapping goes a long way. Yeah. Another two things that I always tell is index what you're going to search, store what you're going to retrieve. Otherwise, yeah, don't mark them as indexed or search. Few other things, consider using SS4O, simple schema for observability, if you're using OpenSearch as a logging solution. Yeah. There is also integrations. Go look at it. I don't have time to explain it. Integrations. And also, we have what is called an ABC template. ABC template is basically packaging solutions for appropriate log types. So let's say if you're using Nginx logs, we have a predetermined set of settings that can be used that comes as a package, and the package already has the optimization. So I think the actual feature is called index context. Yeah, you can look it up, but yeah, you should consider using all those things. But let's say you are at the point where the damage is already done. If you're at a point where the mapping explosion is already there, then how would you go about it? Yeah. So there are two things that you can do. One is, if you're using if you're into logging workload, yeah, every rollover that you do is an opportunity for you to fix your mapping, because it's a new index that can take new mapping. So every rollover, if you're rolling over every 15 days, you get an opportunity every 15 days to fix your mapping. Yeah. But let's say if you're using a flat index, yeah, an e-commerce search, a flat index where you do not have an opportunity to fix your mapping, we have a feature called read from the snapshots, which is basically you can take a snapshot, put it elsewhere, read it from the snapshot, and re-index it onto a different index. And this index should have the optimized mapping. Yeah. So let's say now you have gone through the hoops and you have done the mapping optimization. What does it lead to? An optimized mapping leads to having more documents on the same shard. So if you had 50 million documents in a 50 gig shard, now all of a sudden you're able to have 100 million documents in the same 50 gig shard, right? So that would lead to reduced shard count. Reduced shard count is going to lead to reduced CPU usage. We saw the ratio in the previous slide. Yeah. Reduced CPU usage is going to let you do scale in or scale down. And this one is going to lead to the title of the stock. Yeah. The other way to look at it is mapping optimization leads to leaner segments. Leaner segments lead to faster searches. Faster searches, as we saw in the previous slide, would lead to reduced CPU usage and reduced memory also. This will lead to, once again, scale in and scale down, eventually to the title of the talk. Yeah. Moving on, so Priyanshi and I, when we were putting this deck together, we thought, okay, we will pick a lot of topics from the best practices documentation, right? But then why would we talk about things that are already documented? I know a lot of people consider the documentation for OpenSearch to be really bad. Trust me, I lead the pack. I always say documentation is not so good. Yeah. But I must say, with the latest look that I have with the documentation, I would say we have come a long way. Yeah. Just to give you an example, the Amazon OpenSearch documentation has this best practices subsection of 4 pages. Yeah. I always recommend my customers to give it a read top to bottom. Yeah. Don't think about if certain things are applicable for you or not. Just give it a read. At the end of it, you should be able to relate topics with your workload. Yeah. And we also have separate sections for tuning search speed. We have a separate section for tuning search speed, ingestion and the search. And for the search, we also have new features like the concurrent segment search and the tiered caching, yeah, and the start tree index that Pallavi talked about, which is a pre-computed aggregation, which makes your aggregation run faster. Yeah. Once again, everything would lead to following the best practices would eventually lead to cost optimization. That is, once again, there's no magic to it. Yeah. And if you're using KNN search, once again, there is a separate section for KNN search optimization, be it the different quantization technique that you see on the screen, or a separate performance tuning part for both the search and the indexing for vector search. And if you want to implement the semantic search and you did the math for your KNN memory requirements and your budget is not within the range, you can also consider using neural sparse search, which is once again a semantic search, but does not use the dense embedding models. It uses the sparse models, uses tokens and weights. As efficient as, or closely efficient to BM25, yeah. So you can consider using neural sparse search as a getting started into the semantic search part of it, yeah. We also have predefined sparse models that we offer with OpenSearch. Moving on, there is also a lot of system configurations, especially if you're self-managing OpenSearch, be it disabling swap memory or U limits or your virtual memory. Everything is documented. Yeah, make sure you give it a read. Make sure you put in a checklist and make sure that you follow them. Yeah, that way you have a well-oiled OpenSearch cluster. Yeah. Okay, so moving on, very conscious of time, and I spoke about effective query writing. Jason is here, who's going to talk about taming your query, I believe, yeah, later in the day. Trust me, I can talk about this query optimization thing for an entire day as an 8-hour workshop, so I cannot do justice here. But these are few of the things that we always recommend, yeah. Understanding the difference between match query and terms query. For example, if you're searching for Kubernetes namespace, there is no reason you should be using match query because you're not expecting relevancy. Yeah, you want the query to be cached well. You want the query to be using query cache, and that's why you use filter context, and you use filter context via terms query. Yeah, so you need to understand what kind of search you're doing and use appropriate query types. Just because your query is working and it is giving you the results that you're expecting does not mean your query is efficient. Just like in the SQL world, right? You can, for the same table, you can write n number of SQL queries, but there is only one, the most optimal way of writing your query. Yeah, so that's where I'm going at. Yeah, some of the do's and don'ts: avoid painless query when possible. Yeah, avoid nested documents when possible. Yeah, so. Another thing that we often see is, the nested aggregation with high cardinality at the top of the chain, which is basically if you're doing group by, group by, group by, group by as a nested aggregation. And if you're having high cardinality field at the top of the chain, this is going to be a super expensive query. Yeah? So consider those things when you start writing queries. Yeah. Okay, so let's talk about the cache efficiency, writing a cache-efficient query. So there are a lot of caches in OpenSearch: request cache, query cache, field data cache, and there's also file system cache. We also have tiered cache. Understanding what kind of query component uses what kind of query cache or cache is important. So that way you can write your query accordingly. Yeah. You also look at the cache eviction rate, the hit ratio. If your hit ratio is too low, that's a symptom that you're not writing cache efficient query. Yeah. So look at the cache metrics, hit ratio, eviction ratio, and all those things. Rewrite your queries. Yeah. Also, okay, we do not have time to look into the other things. Few other things, yeah. You can bend over backside writing all the queries. In spite of it, your search performance is still bad, and that is because sometimes it's not the query itself, it's the data model. Yeah. So consider remodeling your data if there is a better way to model it. So what I always preach is store it in such a way that it is very easy for the search to be accessing your data really fast. Yeah, because it's a search engine, yeah. So which means it has to access data really fast. So index it, model it in such a way that your search is able to look up the data really fast, yeah. Few other things, yeah. Delete by query versus delete by ID. When you run delete by query or update by query, what internally happens is it runs a query, the query that you gave, it fetches all the IDs meant for that query, and then it issues a delete by ID request. You might as well, if you have the ID in your hand, might as well use the delete by ID. Yeah, goes to both delete by query and update by query. This situation is quite bad, I would say, to an extent where I have had 2 engagements where there's a lot of performance problem. We had workshops going through a lot of different things, but at the end, it was just the delete by query or the update by query that was the problem. Just by switching it to a better mechanism, the problem, every other cascading problem were solved. Yeah. Time's up. Okay. I have a lot of things to say, but one other thing that I would say is if you're using rollover index, yeah, 5 minutes? Okay, okay, perfect, yeah. So if you're using a lot of rolling index, especially for logging data, right? And you have, let's say, 30 days worth of data, and every day you produce an rolled over index, yeah, now you have 30 different indices. And a search is coming in, asking for last 8 hours worth of data. So you can pretty much guarantee that the data resides in your current index and not in your rolled over index from 20 days ago, all right? But when you run a search, you are running the search on the alias, which is actually targeting every index that is there, all the 30 days, yeah? So what internally happens is there is this scan match pre-filter search, which basically looks at, it runs a pre-filter search, which looks at those indices that, and it checks if the index has the data for it or not. So last 8 hours is the request. An index from 20 days ago pretty much is not going to have the data, so it's a pre-check to cancel any search request that is going to that index. So basically what you can see is the skipped data that is marked here should be really high, especially when you're searching for the last 15 minutes or last 8 hours, right? When you have a logging situation and you actually do not see skipped happening, which is an indication that your query probably is not written correctly, which is the range query that you see here, or your field type, the data type that you have used itself is incorrect, yeah? Or something else is going wrong. That is the takeaway, yeah? So you have to see skipped so that you do not request to perform a search on an index that you pretty much know that there is no data for it for the given query, yeah? One other thing that I would say is this one, right? So let's say you have a lot of, your search is systematically slow everywhere, right? Systematically end-to-end, yeah? How would you go about it, yeah? So one thing, if you're on the Amazon managed service, the one thing that I would request my customer is to run a log insights query, enable slow logs, prerequisite, yeah? run a log inside query something like this, which is going to, and sort it by took time, which is going to give you a list of queries from the most bad performing to that order. So go after those that are really bad. And pretty much, if you're, let's say, running an alert query, which is quite bad, this is going to be repeating every 5 minutes or whatever it is, So by going from top to bottom and conquering it that way, you can, by the end of, I don't know, 10th or the 15th query, you are, addressing a lot of similar queries coming in that are bad queries, So log inside, so slow logs, logs inside, and then once again, once you have identified the worst of the worst query, profile the query. Profile the query, which gives you the breakdown of the query, understand which of the query component is bad, and go after the biggest chunk of the problem, One other thing that you can do to find the bad performing query is the previously shown query insights. I think available from 2.19 onwards or 2.17 onwards, and the 2.19 we have already added the UI for it, which can also give you the bad performing queries. And as you see here on the screen here, it also gives you a breakdown of the query phase and the fetch phase. It also gives you that level of detailed information. Let's see what else. Probably this is the last thing that I'm going to say because of the time, right? One other thing that we often see is when you write a really bad query, let's say really bad that it runs for 10 minutes. You might ask, my client timeout is 60 seconds, so there is no way a query can run beyond 60 seconds, right? But then if you look at it, right, the client has closed the connection, does not mean Lucene has stopped executing the query. So which means it is still running in the background for 10 minutes, 15 minutes. We have seen queries running for like 1 hour or so. So how do you, and it does not appear in your slow logs because it has not failed. A failed query will never show up. A running query will never show up in your slow logs. So what you can also do is use the cat task. I have the API call that I use regularly, but you can also use other query parameters, which basically tells you what query is running for how long. As in this example, it's only 2 seconds, but what I always recommend my customers is run this cat task every 5 minutes or so, right, and catch the super long running queries as it happens. So you can find the offending query and, find the offending party and ask them to stop executing the query, especially if it's an alert query that has been set running every 5 minutes or every 10 minutes, right? There is no trace of it, who's running it, So, so this is one way to identify at least when a bad query happens. 1 minute left, okay. So, I'm just name dropping some of the features that we have, once again, that can be used for cost optimization. Once again, cost optimization is not a magic. Performance tuning is what you need. And when you do it right, you get cost optimization. I don't have to go through this, but the one thing that I will say is there are so many new things happening with OpenSearch, So much so that I had to add something new in the last 30 minutes in the slide, which is something that I missed. The last thing that I would say is when you do performance tuning, also consider doing one thing at a time. Do not do everything in one go because you do not know. There's no way to track what performance tuning that you did and what is the influence of it. Maybe some of the tuning that you do is not working. Maybe it is working against you. So in order to track, it's always best to do one thing at a time, understand the performance implications or the betterment that it has or the lack of it. No time for questions, but we are outside, so Cash is outside. There's a lot of things that we did not discuss here, but questions can be asked outside. Thank you, and thank you, Priyanshi.